Let's now give several examples. Encryption is not a new technique. From the beginning of history, people tried to hide and encrypt all sorts of information. A good example of this is Caesar's cipher, which will be brought up on more than one occasion later. Caesar's cipher, which according to historians was really used by Julius Caesar, was a code designed to hide an intended message, for example, battlefield commands, in a ciphered way. Messages would be encrypted using a simple technique. Letters would be shifted by some number of positions, for example, 3 positions. If a shift of 3 was used, D would be written instead of A. The algorithm's key in Caesar's cipher is the shift number. This encryption method is extremely weak for several reasons. Above all, the key is very short. To test all possibilities, it's enough to check 26 shifts, the number of letters in the alphabet. When running permutations, you'd need to see if the result forms an intelligible message. And apart from this, the ciphertext would reveal much about the plaintext. Some plaintext data will always be revealed. Length is a good example. The longer the ciphertext, the longer the plaintext is. This can be assumed on a one-to-one relationship. It's practically linear. This is inevitable to a degree. If you don't want this information to transpire, you'd always need to generate maximum length ciphertexts. This solution is implemented in cryptography practically only by 3-letter agencies in the US. The machines in these agencies are hooked by a specially dedicated link that is used for incessant pseudo-random data transmission. If you tried to listen on this link, you'd not be able to discern neither the beginning nor the end of an intended message in the noise that complements transmission. The point is that Caesar's cipher reveals also other information. Letter frequency distribution is a trait shared by all languages. Some letters are more or less common. It's easy to check this. If you use an encryption method similar to Caesar's cipher, some characters in the ciphertext will come up more frequently. Using this assumption, it's really easy to deduce the plaintext representation of the most frequent ciphertext letter. Caesar's cipher was an example of a weak encryption technique. At the other end, there's an all-out ideal solution, one-time pad. It's ideal on several counts. First of all, it's impossible to crack. The encryption makes use of a one-time key, a pad. A key is never reused. This is the first of the requirements that are hard to ensure because the difficulty connected with computer generation of pseudo-random numbers. The second requirement is even harder to meet. The key must be the same length as the plaintext. If this condition is satisfied, if you have a 200-character message in a 200-character random key, encrypting the message is trivially easy. It's enough to perform an XOR operation, exclusive disjunction, with individual key and message bits. The result of the XOR operation is 1 only if the values of 2 parameters, key bit and message bit, are different. If the bits are the same, the result is 0. Something is altered, but this can be reversed. At this point, this is vital for us. A message that is encrypted using one-time pad doesn't reveal any information about the key or the plaintext message. So why isn't one-time pad encryption in universal use? This is because the cipher's applicability is very limited. They depend on the possession of a pseudo-random key. Even if it appears otherwise at first glance, all computers used today, quantum computers are not yet available, are always deterministic. They don't have access to any random operations. Even if it doesn't seem so for a user, they always go through the same operations in a given situation. So how can you generate or ensure the required random information? This is a serious issue that can be solved in a range of solutions. The first concept involved it being brought from the outside, from physical phenomena. If a computer would be, for example, able to measure outside temperature with high accuracy, count the flies that sit atop a building, and divide one by another, the result would truly be random, not influenced by any other factor. But computers aren't capable of doing that. Random number generation could also be provided from keystroke timing. This solution was widespread but quite weak. The intervals between individual keystrokes from a good and systematic typist are deterministic. Pace variation is in the order of milliseconds. And advanced typist keystrokes dynamics always have the same flow and speed. Another source is mouse cursor coordinates. A generator can use a saved coordinate. Assuming that a user's operations vary, this solution truly provides relative randomness. But what if you need a random key directly at system startup? An operating system needs to generate a 128-bit key before a user moved a mouse a bit or submitted enough keyboard input. This is alleviated by hardware solutions. Some chips can measure physical parameters with high accuracy: temperature, electromagnetic radiation, signal rate, and so on, and use the values to generate random numbers. This type of hardware isn't popular yet, so there are still problems with random number generating. If a system has collected some amount of pseudo-random complicated information, they have to be distributed and managed economically. They can't be distributed out for the first long key. There's also another problem with encryption. If a recipient is to decode an encrypted message, they have to be provided with a key. There's no other way around it. The message itself is 100% secure. How to forward a key to a recipient in a safe manner? Use a trusted channel. But key length is equal to plaintext length. If you have found a trusted way of exchanging a key, why encrypt it in the first place? You could have directly transmitted it over the secure channel. One-time pad, although sophisticated, is impractical. Let's try to strike a good balance between Caesar cipher and one-time pad. The next parts of the lecture will be dedicated to this. The ideal will be the same each time. A key has to be significantly shorter than the information that is protected using the key. The assumption is that it's less demanding to protect and exchange a relatively short key than to protect and exchange a potentially long message. Think of protecting a car. Preventing the theft of a car, if it's otherwise unprotected, might be quite difficult. It's much easier to protect the car with a key that you take with you everywhere. You assume that if you have the key, the car that it is used to protect is also secure. The module will talk about the characteristics of symmetric encryption and discuss the flaws and strengths of this solution. We'll review block cipher modes, or in other words, tell you why even the most secure symmetric ciphers will fail if ill implemented. An alternative to block ciphers, stream ciphers, will also be included in the guide. We'll touch upon stream ciphers' insecurity and tell you why the number of their applications is thinning. Another problem covered will be public key cryptography or asymmetric cryptography, a cryptographic field with a much shorter history. While symmetric encryption was used back in the days of Julius Caesar, public key encryption has emerged quite recently. It's about 100 years old. The practical applications of this solution are even newer. We'll also discuss why asymmetric ciphers aren't good for encrypting long messages and broach the main shortcomings of asymmetric ciphers. Another topic will include hashing functions and their mode of operation, and tell you why calculating a hash function doesn't ensure a vital data aspect known as non-repudiation. Non-repudiation was mentioned earlier in the modules. We'll tell you what other methods can be employed to guarantee message non-repudiation and how this is achieved. Or in other words, how does a digital signature work? At the end, we'll also discuss a way in which three basic algorithm types, symmetric ciphers, public key ciphers, and hash functions, are used together in modern cryptographic systems. See you in the training.